So, good afternoon, everyone. Today is January 26, 2026, and we are wending our way through statics, ES 2110. When we take a look at our work together, right now we have completed chapter 1 homework, which was not chapter 1. If you read through it, there really was no homework. It was a handout that I gave you, talking about conversion factors. And I have graded that. And I don't know if you read this handout, but there are some stories about famous unit conversion errors. And these are true stories, by the way, I mean, they're unbelievable, but if you ever think I'm kind of a hard case when it comes to units, you'll understand why after you see some of the major things that happen. One of the stories that I heard about engineering is, it was a comedian, but he said, nobody ever cares what you do until you mess up. So like if you make millions of dollars and save millions of life, you get an attractive framed certificate of achievement. And if you mess up, you make the headlines. So we don't want any of that to happen, right? But NASA actually, crashed an orbiting spacecraft into Mars. And so we talk a little bit about that. Tokyo Disneyland Space Mountain axle broke, causing it to derail. And this is one of my favorites. The Air Canada flight 143 ran completely out of fuel halfway between Montreal and Edmonton. And it was because the fuel load was miscalculated. What had happened was, Canada, as our neighbors to the north, have always been subjected to using both the SI system and the US customary system. And the airplane that they were flying had just been, it was either a new airplane or they had just refurbished it, but they changed units on fuel. So here's a question, just an aerodynamic engineering question. Why is it that you suppose airplanes do not fly with full fuel tanks? Because what's that?
It's heavy.
It's heavy. And what does heavy mean?
It burns more fuel to stay.
That is exactly correct, expensive. So there is a calculation plus a margin of safety. But when you realize that there are 2.2 pounds per kilogram, and so you can come out with 1/4, a little bit less than 1/4 of the fuel that you need, plus that you're still gonna run out of fuel. So this was a neat story though, because everybody was fine. But what happened was they called that airplane, it was made fun of for a long time. They called it the Gimli glider because the pilot, who is like the most cool-headed person in the entire planet, in my opinion, saw this abandoned airstrip and at Gimli, and he decided to land the airplane on the abandoned airstrip. But what had happened was, because it was abandoned, there were people, they would have like parties and stuff out there on the airstrip, and there are all these families having like picnic. And there's some little kid who was riding his bike on the runway. And the other part is once the engines died on an airplane, it's very quiet, right? You don't hear it. So he's riding his little bike out there and he sees this airplane coming in. And the pilot actually had to crab the landing, meaning he was too high in altitude and he didn't have enough to glide around again. So he made it less aerodynamic by putting a side crab into it, which is how you land in high wind conditions, which was not approved for this airplane, but he thought, well, maybe it'll work, and it did. But he landed the airplane. And a little kid like yelled at everybody, get off the runway, there's a plane coming in, and they all left. And so nobody got hurt. But when the pilot landed the plane, he had to apply the brakes so heavily. And they also lost hydraulics, because once they lost the fuel, they lost hydraulics. So everything was like, I mean, he was seriously like wrestling a plane, right? So when he landed, they hit the brakes so hard that the nose gear and the main gear rolled up the pavement on the runway behind them. They destroyed the pavement on the runway, and the nose gear caught on fire. So they came to a stop, and the pilot said, I'm not going to lose this airplane after what I've just gone through. So he jumps out with a fire extinguisher and puts out. I mean, this is the guy you want on the plane with you, right? You know, this is like serious stuff, but he put out the fire, everything was fine. But that is like one of my favorite stories because, first of all, because everybody lived, and second of all, because it's a mistake that is so easy to make. So,
Further convinced me that we should not be converting when we show up. We're
yeah,
just gonna have to get hired in Germany.
Yeah. but you know, that's it, but we had, you know, but this is America and that's how we do things, so I know. And then the other part is, of course, even in Germany, they have to cope with it because we are America and we do it, and so they have to do it too. But you're right, the logical thing would have been, when I was at Immaculate Conception Junior High back in the day, and my teacher, my math teacher, had a big bumper sticker that said think metric, we should have started thinking metric, but we chose not to, and we haven't changed our minds.
His own used metric. And then they upcharge their customers for making them convert it to- There you go.
That's not a bad idea, you know, that is not a bad idea, but anyway, so. I like that, that is innovative. You know what? And I'm just gonna say this, and I think you have some really good ideas, and somewhere out of that kind of thinking, people are gonna come up with something that actually makes sense. But the big problem is, the good news and the bad news is, we all rely on capitalism, so there really is no us, and there is no they. It's just a bunch of people doing a bunch of stuff the way they want to, so. Anyway, but maybe you're gonna fix that, Jace, so we'll keep our fingers crossed. All right, all right, we'll do it within the next 20 years, so I haven't lost my marbles yet, and I can enjoy the fruits of your labor, so. Maybe 40 years, I'll give myself 30 at least, so, but don't, time is of the essence, Jace, that's right, so get after it, so. Anyway, so does anybody have any questions on unit conversions? The homework I received looked good, so I'm not concerned, but just let me know if you have any questions, because the issue will continue to plague us as time goes on. So this week, I thought I pulled this up, but maybe I have to pull it up again. Something I'm working on. All right, come back over here. So this week, we are going to be working on chapter 2. And in chapter 2, this is just I don't know why it always does that. Those blue lines always come out like that when I photocopy. When we start talking about chapter 2, what we're really going to do is to get into the real kernel of truth, the nuts and bolts of vector mechanics. Okay, so when we're working on chapter 2, I think we have a couple of weeks. Let's just double check. Or did I give you 2 weeks on chapter 3? So. That's your quiz. There it is, January 30th. Oh, so it's this Friday. So, okay. So, and once again, if you're a day or two late, I'm not going to notice, but do get it in over the weekend. So chapter 2 is really where we start talking about the nuts and bolts of how vector mechanics work. And this is going to be the topic that we're going to expand upon for the rest of this class. Okay, at least for the first 6 chapters. So please pay attention. The other thing, and I do not say this lightly in any way, is I'm gonna write it down here. I've already said it. Do not use the triangle nor the parallelogram method to solve problems. Those methods will get you nowhere in the future. Every problem, even if it says use the triangle or the parallelogram method, use resolution of vectors into components.
I do not know what any of those is.
Well, you will. But I'm writing this up front just to preface it. So so let's take a look at the textbook, probably the easiest way to get started, all right? When we start talking about the addition of planar forces, the first thing is, I want you to be reassured, in this chapter, we are only working with things in 2 dimensions, so in a plane. The plane can just be the chalkboard or the blackboard or the whiteboard, for example. And generally speaking, when we look at a force in 2 dimensions, we refer to that force as a vector of some sort acting in the X and the Y direction. There are some changes to that, but this is very similar to what you've done in trigonometry or in calculus, okay? So we have forces in the X direction and forces in the Y direction, okay? So when we talk about this, we not only talk about in the planar, which we will extrapolate later on to 3 dimensions, so space. And then we also talk about forces acting on a particle. And we will extend that idea to working on a rigid body or shape, okay? But when we have a particle, no matter what the forces are acting on, we have a boat, some tug lines, we consider in our most uncreative engineering way that the boat looks like this, okay? Boat looks like this and it has some forces acting on it. All right, we have a bookcase, we have some forces acting on it. Guess what the bookcase looks like? This, right? So, okay, no matter what, we're talking about a point in space. The reason we do that is because if you act on something that has a shape, that shape can actually tip or roll, okay? So to start our discussion, we look at things that do not tip nor roll. They also don't deform, but that won't come till next year when we talk in mechanics of materials. But basically, a point in space acted on by forces can neither tip nor roll nor deform. All can do is move, and that movement is called translation. So in statics, where we want things to sit still, we start with Newton's second law, which says force vector x is equal to mass times acceleration. And if acceleration is equal to 0, we can say that the forces acting in a given vector direction equal to 0. Well, that's really no fun, right? At that point, what do? Well, the answer is and sum up forces acting on something. For example, this stapler has the weight of gravity acting down on it, or it is acting down with the force of gravity. Why is it not falling through the table? That's right, exactly. It's called a normal force is pushing up, okay? It's the same with the legs on these tables. It's the same with anything. If it's not moving, the sum of the forces acting on that particle will be equal to 0 in that particular vector direction, right?
That means that there are individual components, they just equal out to 0.
Yes, in each vector direction. In other words, this is not moving. If I were to, if it weighs this much and the force is acting downward, and I push on it this way with that much force, it's still going to move, even though the sum of those scalar forces would be 0. There's no point in summing scalars. You always sum vectors. So you're always talking about stuff that happens in the y direction equals 0, stuff that happens in the x direction equals 0. Okay, but they don't ever cross. So when I talk about not using parallelogram nor triangle method, but to use resolution of vectors into components, this is what I'm talking about. This in 2 dimensions for a particle turns into this. The summation of forces in the y direction equals 0, and the summation of forces in the x direction also equals 0. And if these 2 conditions are not met, the particle will move, will translate. Are there other kinds of motions? So many other kinds of motions, but this is all we're talking about right now. Okay, so this is where we start talking about, if you look in your textbook, you'll see that this is the parallelogram method, where we have a particle A. hang on just a second. I wanna make sure I'm sharing the right thing. If you look at your textbook, you'll see that here we have a particle A that's being acted on by two forces, P and Q. Now, P and Q in this particular case are not opposed, so you could probably suggest that that particle A is going to move, and since both of these forces are acting toward the right, it's probably going to go toward the right in a direction that's in between those two forces, right? Just spitballing. Well, you could also think about A as being acted on by a single force, which is the vector sum of P and Q. All right, so in other words, you could break P down into P sub X and P sub Y, their components, and the same with Q sub X and Q sub Y. Then you add P sub X, Q sub X, that would be the X component of the resultant force. You could add P sub Y and Q sub Y, and that would be the resultant in the Y direction. This is the vector resolution method. This is the parallelogram method, where you do a sketch of the vector, and then you draw a force that goes, you make a parallelogram that has one leg, one side that is parallel to P, one side is parallel to Q, and you draw from point A to the other, the opposite vertex, and that is the resultant force. This is the method that will get you nowhere in life.
Why?
Because you can't do it in 3 dimensions.
So why did we teach you?
I have zero idea. Because in the old days, perhaps, making this up, this was even before my time, if you can imagine, there was no, maybe they didn't have calculators, maybe they were drawing things to scale. If you're doing scale drawings, this works well in 2 dimensions. It never works well in 3 dimensions. This always works well, whether you have a scale drawing or whether you're doing a little silly sketch. But you can always do it as the sum of result, as creating a resultant based on the vector components. All right, so how do we find the vector components? Well, the first thing is we need to come up with a little bit of ideas about how we're going to write this stuff, right? How do we write vectors? Vectors are magnitude and direction. Scalars are magnitude only. So if I say I'm driving my car and I'm going 70 miles an hour, that's a scalar. If I say I'm driving my car and I'm going 70 miles an hour to Billings, that's a vector. See the difference? So whenever we add vectors, we have to keep in mind the directional properties. So we're not only adding the magnitude, we're also adding the direction. And the easiest way to do that is to break it up into perpendicular components. And the most common perpendicular components are X and Y. Okay. There are others as well. For example, if you have something going around a circle or a track of some sort, you can break down things into the normal and the tangential. And there's some really cool reasons to do that. You can do a bunch of different things. You can put things on a slant, like if you have a box sliding down an incline, you can break down the forces into what might be called X prime and Y prime. But this is the star of the day. This is the one that we use almost exclusively in the beginning and that we use very commonly as we proceed with our discussion. All right. So once again, when we talk about the addition of vectors, there's one thing that I would like you to notice. Vectors are denoted in your textbook as being bolded letters. So this is vector P and this is vector Q. It's very, yes, sir, please.
If I'm not mistaken, a capital letter, this is what we're doing in physics, so. I want to
Yes.
make sure I understand.
Yes,
Capital letter is just magnitude. It
yes.
has to have a squiggly on it to indicate that it is.
Yes, that's another good point. Your textbook in statics does this for a vector, right? They make it bold. You can see how difficult it is for me to bold a letter, right? So I do a squiggly, like you were saying. There's two main ways to do it. You can say P with an arrow over it, which is my preferred way, or you can do P with a caret over it. Okay, this is the way I prefer to do it. But it means exactly the same as this.
So an unbolded P is just magnitude.
Yes,
Okay.
at least in this class, and probably for the most part in physics as well. But in this class, yes, unless it has, and like I said, I don't draw the P with a bold just because it's very difficult for me to do that. So I do the P with the arrow, but that means it's a vector. So if you have P with a vector and you're using X and Y, you could write that as P sub X. This is how you write it in P sub Y. So you can break it down into those components. And another way to write it, which is something that we do commonly here, is we take the P sub X component and multiply it by a unit vector, which we call I, and P sub Y, and multiply it by a unit vector, which we call J. I just means, for now, it means a lot more than this, but we'll talk about the other meanings and the enhanced meaning of I and J. I just means for now in the X direction. J just means in the Y direction.
So plus Y in the Y direction.
Yes, so P sub P is equal to P sub X in the I direction plus P sub Y in the J direction, which means if this is my P sub X and this is my P sub Y, my vector looks like this. So the other piece I want to explain to you is P sub X plus P sub Y, you cannot reduce this. This is not scalar addition. Okay, in other words, you can't really add the X piece and the Y piece together. If you look up here, if you knew this X piece and this Y piece, how could you come out with the resultant? Or how could you come out with vector P? What does that look like? In trigonometry. So, yes? Hypotenuse, exactly. This is P sub X squared plus P sub Y squared. Take the square root. That is equal to the magnitude of the vector P. Very, very good. Okay. And Jace, that is a place where I would write P without the arrow over it. Okay. This is the magnitude of the vector. That's the length of the vector. Yep, excellent. All right. So the addition of vectors follows some properties that are similar to scalar math, and some properties do not carry forth. For example, vector math is commutative. So vector P plus vector Q is equal to vector Q plus vector P. All right.
One more question.
Sure.
Scalar refers to something that has a number but no direction.
Exactly. Magnitude. That is correct. P vector P minus vector Q is equal to P plus the negative of the vector Q. So we have the negative property. And we also have the associative property where it really does, if you have three vectors added together, it doesn't matter which two you add together first, just like with normal math. Okay, so P plus Q plus S, you can add P plus Q together first and then add S, or you can add Q plus S together and then add P, or any other combination, but it does not matter which one you do first. Okay. Then we talk a little bit about the resultant. If you take a vector, like let's just say I have a tensiometer that will hold 50 pounds in the Y direction, right? Holding it like this, pulls down. If I have three tensiometers, they will hold 150 pounds also in the Y direction. So in other words, you can multiply a vector, which is negative 50Y, by a scalar, which is 3, and those properties will still hold. All right. So there are two things that we do with vectors over and over again, and that you'll do in this class and you'll do in other classes forever and ever. And this is what we're going to talk about today. We can find or solve for the resultant, which means adding together or subtracting from, of two or more vectors. And we can resolve a vector into components. All right, what does that mean? Well, let's just say we have our creatively drawn boat right here. And we pull on it with a force over here. And we pull on it with a force over here. Okay, we could think of these two as being pulled, as pulling on it with a single force R, which I'm not drawing to scale, not to scale. Okay, where the vector R is equal to vector P plus vector Q. That's the first one. We find the resultant. So in other words, we add by components. So in other words, R sub X would be equal to P sub X plus Q sub X, and R sub Y would be equal to P sub Y plus Q sub Y. That is finding the resultant. The other thing we can do is resolve into components. If we have a particle and we're pulling on it with some vector, I'm gonna call it S, we can use a little bit of trigonometry. We know this angle, which is generally called theta. Theta looks like this. It's a Greek letter. It's generally just a typical letter used to denote an angle. Not the only one. You also use alpha, beta, gamma. You can use a bunch of different ones, but theta is kind of like our first pick. So you can resolve this. S sub X is going to equal the magnitude of S times the cosine of the angle theta, because cosine is adjacent over hypotenuse. Adjacent is in the X direction. And S sub Y is equal to S times the sine of theta. Okay, so this is called resolving. So we have resultant and we have resolving. And those are like, you can see that they're highly related to each other, right? They're very much related to each other, but in each case, it involves finding the X components and the Y components or whatever. And like I said, you can use other coordinate systems, but for the most part, we like to use X's and Y's. Okay. All right, let's take another little look here at the book. All right, so trying to think if there's any. So here we go. Here's sample problem 1.2. And it says we have two forces, P and Q, that are acting on a nail head. It looks like maybe we're trying to pull out this nail head. And they say determine their resultant. Okay, now I'm going to go ahead and work this problem for you. You can see that they use the parallelogram method. And when are we going to use the so just from my, are we going to, Ryan says, no, I don't know what we're going to use, but we're not going to use the parallelogram method, right? So if we wanted to work this problem, what we really want to do is to take the force P and resolve it into components, and take the force Q and add it to resolve it into components. So I'm going to show you how to do that. All right. I'm told that Q has a magnitude of 60.
Are we going to have to do this?
Yes. Not in this chapter. Yes.
But eventually there's gonna be a Z component.
There is absolutely going to be a Z component.
Fun thing that
You use alpha, beta, gamma, theta. You take theta with respect to an axis, theta with respect to a plane, all kinds of stuff. But the easiest way to do it, and this is really hard for some people to accept, but I will taught this a whole lot of number of times, and I've taught it to many different types of people. Even if you have exceptional spatial reasoning, the best way to do it is to resolve it into X, Y, and Z components every single time. That is the way that will work every single time without you having to look for a trick. So once again, when we get to that point, I will teach that to you, just like I say, do not use the parallelogram method or the triangle method. I will say, do not use these other spatial reasoning techniques. So we're going to get you through it. Now, in the future, in the rest of your lives, do you guys understand? I mean, here's another question. Are you guys familiar with the idea of spatial reasoning? Okay, well, this is a skill that can be developed. So I'm going to take 5 minutes and talk to you about it. So spatial reasoning is a very, very big deal. And the reason what spatial reasoning is just sort of having a feel for the way things look, right? That's on a basic level. But how you develop spatial reasoning, if you're a typical person, is you do things that involve spatial reasoning. You work on engines and you have to get underneath it, or you learn how to sew, and you have to take a flat piece of material and shape it into a garment that's going to become a three-dimensional garment on a human being. Or you shoot lawn darts in your backyard without killing people, you know, I mean, there's all kinds of ways that people come to it. But in general, some people, when they come to college, have developed their spatial reasoning ability, and some people have not. So that's kind of an unfair playing field, right? I mean, if some people have really good spatial reasoning and some people don't. So if you have good spatial reasoning, it's going to serve you well for the rest of your life. If you don't, we have ways of resolving things, not resolving, there are ways of working things out without having to have high degrees of spatial reasoning. And I have learned, much to my own surprise, that the methods for doing it without having high spatial reasoning are actually better for everybody. They're easier and more reliable for everybody, regardless of your level of spatial reasoning. I would give you 2 examples of spatial reasoning. I'll tell you one other thing. So guess if you divide, like educational statisticians have divided all sorts of innate properties and learned properties among college freshmen. There are 3 groups of people who have the highest spatial reasoning coming into college: engineers, architects, and artists. Okay, so what do those 3 people have in common? Spatial reasoning. That's it. So in other words, it's just one of these very things, but it's very interesting because people who have high spatial reasoning tend to go into those professions. So some of them, if you have high math skills, you might go into engineering. If you have high creative ability, you might go into art. Or I've had a lot of art students go into engineering because they don't want to work as insurance agents. You know, I mean, there's just all kinds of different reasons that people do that. But, and when I say that, what I mean is there's this expression, starving artist. There is no expression, starving engineer. So that's the other piece of it. So a lot of people go into engineering because there is an outlet for your creativity that's not going to involve you working a different day job to support yourself, because you will support yourself doing your creative endeavor, which is cool. Anyway, so like one time, and I'll tell a story of myself, I was testifying as an expert witness on a particular example, and the lawyer asked me how tall something was, and I said 16 feet. And he said, "How did you measure that?" And I'm like, "Well, I didn't measure it. I just know it's 16 feet. And he goes, "How do you know that?" And I kind of sounded like, I kind of got mad at him because I'm like, do you not ever look at berms? They're either 8 or 16 feet. What would you think it is? It's not a good thing to say to a lawyer in court because it makes them upset. But I wasn't in court, I was in a deposition. But that's what spatial reasoning involves. Some people can look at something and see if it is, 16 or 8 feet, and some people really can't. So some people, you know, you go somewhere and you can see how long it's going to take you to go somewhere, because you can think, well, that's about a mile away, and other people have no idea, and you will know instantly when you're with people like that. So this is what spatial reasoning is about. However, regardless of how super duper your spatial reasoning is, much like me informing the lawyer that he was an idiot, couldn't tell that it was 16 feet tall, not being able to do it mathematically will not serve you well. So that's how we're going to do it. Okay, so anyway, so let's take a look at these two forces.
What do you want you to pull out like an angle finder and measure the shadow
He-
versus the sun?
He wanted me, which is fair, to have some documentation that said I measured this with a tape measure and it's 16 feet tall. And he didn't have the sense of, they're never 12 feet, 4 inches tall, right? I mean, they're either 8 or 16 because that's how components come. So he didn't know that. And
What is the component we're measuring?
it was a type of a berm. It was a type of a barrier for a water. Yeah, so anyway, there's a long board
So
story.
you knew it was either 8 or 16.
Right,
And it
but-
wasn't 8.
And I've never really articulated it. See what I mean? That's exactly right. It's exactly what you just said. So, but better to do the math. So, and I should have had a piece of paper there that day, but I didn't because I measured it with my experience, which was not helpful to anybody. All right, so here we go. We want to know what the resultant is. All right, the resultant of this force is going to be the vector Q plus the vector P. All right, what is the vector? Let's look at P since it's down here. Well, we know that P makes a 20-degree angle with the horizontal. That means that my P sub X is going to be the overall magnitude, the hypotenuse, 40 newtons times the cosine of 20 degrees. Similarly, we know that P sub Y is going to be 40 newtons times the sine of 20 degrees. What about Q? Well, the angle is a little more complicated, isn't it? Because I don't want to measure it from P. I want to measure it from the horizontal.
Are you
which-
making 25 from P?
I'm measuring 25 plus 20. Right, this is
So
25.
25.
You got it. So Q sub X then is going to be the magnitude of that force, which is 60 newtons times the cosine of the entire angle, which is 45 degrees. And similarly, Q sub Y is going to be equal to 60 newtons times the sine of 45 degrees. All right, well, all of these are numbers that I can cope with. Yeah, so that's a good thing. Except for I didn't bring my calculator, so I have to do it here. What is the cosine of 20 degrees? Because otherwise, oh, you have to make sure to say, you have to say degrees, because what is the SI unit for degree, for angles? Radians, just radians, but there's only pi 3.14 radians in 180 degrees. So if you don't make sure that your calculator is operating in degree mode, it will return radians unless you've set it differently. So this one, P sub X is going to be 40 times this number, 0.93969, blah, 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 newtons. And let's come back here and get the cosine of 45 degrees, which should be, there it is, 0.707. That's famous, right? Do you know why? Because it is the square root of 2. 0.707. And also the cosine and the sine of 45 degrees is the same, because the opposite and the adjacent are equal to each other. So if you type in sine, you'll see there it is, 0.707. So up here, we get 60 times 0.707 newtons. And here we got 40 times the sine of 20,
Is that why,
0.342.
is that why the internal length from corner to corner of any square of length A is A squared?
It is. Isn't that lovely? Isn't that just peachy? You know, one of the cool things about engineering is you'll start to see all these things that just happen. Like, why do we always use, these are called orthogonal coordinates when they're perpendicular to each other? Why do we do that? Well, because a squared plus b squared equals c squared. If you have a non-orthogonal coordinate system, which you can, you have to use the law of cosines. So you have to go a squared plus b squared minus 2ac times the cosine of the angle between them. What's the cosine of 90 degrees? 0. Yes, so it all goes away. Isn't that cool? So yeah, very nice stuff. All right, so let's take a look. P sub X then is going to be 40 times 0.939, blah, 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 right? 40 times, this is what happens when you don't bring your calculator. So this is gonna be 37.56 newtons. And Q sub X is 60 times 0.707. 42.42 newtons. And up here, 40 times, oops, 40 times 0.4, excuse me, 0.342 is equal to 13.68. Let me write that one down, hang on. 13.68 newtons, and Q sub Y is equal to 60 times 0.707, which is 42.42, which is the same as this, which is what you would expect. Let's get my zoom up here so we can look at all that work. Okay, there it is. Okay, so now we have P sub X, we have Q sub X, we have P sub Y and Q sub Y. Since R is equal to Q plus P, that means that R is equal to R sub X, I, plus R sub Y, J, which is equal to P sub X plus Q sub X, I, plus P sub Y plus Q sub Y, J. So we can just add these two numbers together. 37.56. And this is 79.98, which is basically 80 newtons in the I direction. Plus these two numbers added together. 42.42 newtons plus 13.68 newtons, 56.1 newtons in the J direction. And that is my resultant.
I'm still confused about why we're using combination J.
We haven't discussed it. We will discuss it more and more. Technically, I is a unit vector in the X direction. Unit vector means I have length of one in a direction. J is unit vector in the Y direction, has unit meaning it has length of one. So it's a little vector with length of one in the I direction. If you multiply any number, any scalar by one, what does it become? Yes. Then you add the directional piece and you get the direction. So you can take a scalar, which is the component, multiply it by the unit vector in that direction and bring it back to being almost a vector.
So these are newtons without any length.
I and J, no, they're just directions. They don't have any unit at all.
What would be an example of them having?
I and J never have units. They are
I mean, like, if the vector had units, instead of being I.
like this. That means that 80 newtons in the I direction or in the X direction, 56 newtons in J direction, which means if I had P plus Q, let me draw this. Here's my X direction, here's my Y direction. My resultant vector is 80 newtons in the I direction and 56 newtons in the J direction. So
That seems so
this
dumb.
it's dumb right now, Jace, because we're not talking about everything it means. As we continue our discussion, as we wend our way through the journey of statics, we will learn more and more about it. And which is the unit vector using groups. I'll also use E and E sub R and E sub theta and all kinds of other unit vectors. So they become very important to our discussion, but I introduce it without discussion at this point so you can start working with it. So at this point, this is true, but it is not complete. When it has an I after it, it's in the J in the X direction. When it has a J after it, it's in the Y direction. And then it will mean something else later. Okay. All right. So let's just take a look at our home page, our course page here as we finish up today. And what we see is, there we go, that our topics for this week, we've watched videos 1, 2, 3, You watch videos 4, 5, 6. Since you're here, you don't have to watch this video, but I will have it up as today's lecture on our page. So if you have any issues of confusion, you're welcome to watch it again, but you've already seen it, so you don't have to watch it again. And then by the end of this week, oh, wait a second, no, yeah, it is by the end of this week, sorry. You should have watched 1 through 6. This week, we're watching 7, 8, and 9. I apologize for that. So homework number 2 will be due. And then the next week, we will be working on quiz number 1, which actually is just it's just chapters 1 and 2. So there's no new information introduced for the quiz. It's just chapters 1 and 2. All right?
Are the quiz gonna contain questions about the chapters?
Yes. Well, it's a problem that you have to solve. It's a multi-step problem. So they're good question. So what happens on a quiz, you take it by yourself. It's not a proctored deal. But what it is it's a problem. It would be similar to a problem you'll have on your midterm exam. And I step you through it. I give you like 5 steps that you have to complete. Draw a free body diagram, show me your theory, resolve the vectors, something like that.
So it's not gonna be pulled from chapter 2, it's good, or whatever, it's gonna test our knowledge of the things that we.
That is correct, what you just said. And what I do with that is I use the quizzes. You have 2 quizzes. You have one after chapter 2 and one after chapter 8. And what I do with that is I use it as a teaching tool to help you learn the format of what your exams have to look like. Because your exams, which are proctored, you just have a midterm and final, but they are 2-hour long. They're 4 problems. And you're graded. It's not an answer only thing. So it's a graded partial credit on everything. Yes, Ryan.
On the homework, you want us, like, going through the whole 5 steps you have here, like, problem identification. Sketch it, so.
As appropriate, yes. A sketch or a free body diagram is almost always called for. And it can always be just a little hunk like this. It does not have to be elaborate, right? It's just enough to convey that information. Like I said, engineers are like, this is my favorite when we talk about refrigerators, when we're doing thermodynamics. This is what a refrigerator looks like to an engineer, okay? And you'll learn that later, but I mean, so it does not have to be elaborate anyway. Yeah.
But you don't want us listing a theory or principle.
That not necessarily. Just if your theory is almost always going to be summation of forces equals 0 in a vector direction. So, yep. So when you just write down this or these, that would be your theory.
Yes, so kind of like write down the equation.
Exactly.
Right.
That's exactly correct. You got it.